Good afternoon and welcome to Silicon Flatirons, to our conference on radio spectrum pollution. This is the tutorial, which is sort of a part of the preliminary program. My name is Pierre de Vries. I am a senior adjunct fellow here and co-director with Dale Hatfield of the Spectrum Policy Initiative. When we do these quite technical programs, we've had some requests in the past to provide a basis for folks who perhaps are not comfortable or working every day in a particular field. And so we are extremely fortunate today that we have Bob Matheson here to give us an introductory tutorial over the next 45 minutes, and he will be doing Q&A. Bob is retired from NTIA, the ITS lab next door, where he worked since 1957. He was the lead engineer when the NTIA began to actually monitor federal use of spectrum and was involved in the design and operation of the radio spectrum measurement system, the NTIA truck. So there is nobody, I think, better qualified to actually give an introduction to this whole topic of radio measurement, particularly RF noise, than Bob. We're very grateful to have him here. And in fact, we're even more grateful to his family that allowed him to come home early from vacation to be with us here today. Please join me in welcoming Bob Matheson.
Okay, now let me see. I got to figure this out here. What leads it forward, backwards?
I think that one is, that should be.
Okay, good, gotcha. Okay, so I'm Bob Matheson, and I have worked here in Boulder making noise measurements for at least 25 years or so, and that was more like 50 years ago. And it's been 40 years or maybe 40 years since I really have made any noise measurements. So I'm a little bit rusty on some of this stuff too. But it was, I got to say, it was a lot of fun going through stuff that I'd forgotten many years ago and putting it on a PowerPoint. So first of all, this will be kind of a historical review of noise and the way we've measured noise. And part of the reason for that is some of the questions we have about how we do noise measurements today. There's been a lot of historical development in the kind of noise that we're faced with and the kind of measurements we need to make. And the kind of measurements that we can't make easily anymore because the problems seem to get more and more complex. But I hope that the historical development kind of brings that up. And I would also invite you to make comments, ask questions, whatever throughout. This is a kind of an informal thing, even though I've got PowerPoint and all that. So first of all, about me, I worked at NTIA 47 years. I retired about 7 years ago. I started out in 1957 working on radio noise as a summer job right out of high school. And I stuck with it forever. I thought it was just really fascinating stuff. Back in the early days, I didn't know anything. Later on, after I graduated from CU, I did a lot of work in instrumenting some of the follow-on systems. And as Pierre said, then later on, I got into the radio spectrum measurement system, the big system that NTIA used to monitor the use of signals mainly, but lots of interference resolution problems and that kind of thing also. For a few years, I was deputy director of the spectrum division at ITS. And then after that, I got working in what I considered really fun stuff like spectrum efficiency and spectrum property rights and technical spectrum policy and that kind of stuff. So the topics we're going to take, we're going to first talk about the ARN2. ARN, atmospheric radio noise, worldwide measurements of noise from lightning. Particular from some of the talks I heard in the earlier roundtable, people think we couldn't get any money to measure noise, but this was a worldwide network. It involved probably half a dozen countries, involved a lot of stuff. So we're going to talk about how we made measurements then. Later on, we kind of finished that first job there with the ARN2, and we went on to the ITS man-made noise program, measuring from a quarter of a megahertz up to 250 megahertz with a very unique vehicle designed especially to do that. And then recently, ITS has made some kind of hit and miss man-made noise measurements just to get a feeling for how things were going, small scale stuff, and so have other people made some interesting measurements. And then we'll talk about some future questions. Okay. So starting with atmospheric radio noise, it was the measurements were actually made by NBS, the National Bureau of Standards, that had moved out here to Boulder in 1951. And they started, one of their first jobs was building up this worldwide noise network that made measurements at 8 frequencies between 113 kilohertz and 20 megahertz. As you know, these are, you might call them shortwave frequencies or whatever you call them, but these are frequencies that can bounce off the ionosphere and be propagated around the world. So just like the signals could propagate around the world, if there was a lightning strike over there in the middle of Africa in a rainforest, that could propagate around the world too. So the interference propagated around the world just like the signals did, and interference was a really major problem. The impulsive noise from lightning, it could easily make a 60 dB change in the amount of background static. And if you wanted to send a signal and your noise level suddenly increased 60 dB, you might really have problems doing it. So it became very important to figure out when noise was occurring at various frequencies, how that changed with summer, winter, fall, time of day, and all of that kind of stuff. That became a major effort. Here's a picture of a typical ARN2 noise recording station, a little box maybe about 10 feet across, and I don't know how well you can see it, but there are you can see the whip antenna there in the middle of it, and then maybe you can see the radial wires out from it. They're about a 100-foot diameter circle that furnished a ground plane with these radial wires. And I say again, 113 kilohertz to 20 megahertz. That's typically the kind of equipment. Of course, there's all vacuum tube equipment back in those days. We measured the RMS, the average power level, and we measured a quantity called V sub D, or the voltage deviation. And I don't know whether you've thought about this a lot, but when you have a thing that's changing in levels a lot, many dB or many tens of dB especially, it makes a lot of difference what kind of detector function you use, what kind of averaging function you use. The RMS, of course, used it squares the voltage to get power. The V sub D just measures the linear voltage. And when you have a lot of high-level signals, the squaring factor means that RMS increases faster than V sub D does. So because we couldn't do anything better really with the electronics and the general level of development we had at the time, we measured those two quantities, RMS and V sub D, and from that generally you could mathematically invent some models that would say how much of the time the signal was really at high levels and that kind of stuff, what portion of the time. So low levels most of the time, occasional high levels. And you could get a clue to what was reasonable with RMS and V sub D. We recorded those on those paper EA charts. So every one of those frequencies got measured for 15 minutes every hour. Then they would send the paper charts back to us in Boulder here. And we would scale them, or at least check to see that the field workers had done good scaling. When I talk about field workers, there's the major part of the network. We had stations on every continent, including 3 stations in Africa, a number of stations in Europe, South America, North America, not exactly at the North Pole, but one up at Thule, and we have one down at Bird Station at the South Pole, and Singapore, India, Japan, Australia. And these stations operated, many of them operated for more than 5 years, but the first really major report that came out involved 5 years of data from this whole set of stations. Okay. And this is the kind of map we got out, and it shows for a particular 4-hour time block. So there were 6 of these time blocks each day, and those are 5 dB contours there, and 4 seasons per year and that kind of stuff. I won't go through how all this works, but in any case, people who knew how to use these things knew what kind of noise, various frequencies were going to get various times of day, and so if they needed to get communications, they'd switch frequencies and that kind of stuff. Now, of course, the other part of the problem, which this thing doesn't show, but there are similar charts that other people made that shows how well the signal propagates. And you might be able to, so you had to both look at the signal propagation stuff, the noise that was competing with, and then you could choose a frequency. A lot harder than pushing the button on your cell phone, but that's the way things were those days. And of course, HF was really important because there were no undersea cables, there were no satellites, there were no fiber optics, there were no... HF was really it. Either you, I guess you could use carrier pigeons and stuff like that, but HF was the only game in town. And so it was really important stuff. A major CCIR report, 322, was published in 1964, and this report is out of that. And at that point, people for the first time had fairly good data on what they had to do to make HF communications work. Okay, so I say it was largely completed with this report in 1964. After the Cold War ended, the Russians and the Chinese also released to us similar data that they had in 1985, TR-85 173. A report was revised with the Russian and Chinese data. And really at that point, the problem was done about as well as it could be done. Now, since then, of course, as I mentioned, satellites and optical fiber and higher frequencies and all that have really taken the importance out of HF. Why would anyone do it the hard way when there are a lot easier, better ways to do it? And so most people have moved away from HF. The ones who have stayed with HF have often done something like this automatic link establishment stuff, where you don't just have a single frequency, but you maybe have 3 or 4 or a half dozen frequencies, and you continually monitor how those channels are working on it. So that when you need to talk to someone somewhere, you just look at your list of channels and see which is working best in that direction, and you tell the system to use that channel then. So the ALE stuff, the automatic link establishment stuff, is kind of a modern way of doing that if you really do have to use HF. Okay, so that was our ARN2 program, and as I say, it essentially ended in the mid-60s, or then there's follow-on work in 1985. But after ITS finished work with the ARN2 stuff, frequencies below 20 megahertz, then there was a major effort. I'm going to talk about something else first. So the question is, how do you make good measurements of noise when noise is a bunch of random impulses? Every time you get a lightning stroke, you get a batch of impulses from that lightning stroke. Some big, some small. So how do you best measure this bunch of random impulses in a meaningful way? And now I've said already that we gave up measuring real details of this, but what we did instead was measure the RMS and the V sub D. Here we have some much more recent data. Oh, and we did that in a 200 hertz bandwidth, so a very, very narrow bandwidth. And one of the reasons was that at HF, you couldn't find any frequency that was clear of use. And so we were lucky we could get a little sliver of 200 megahertz wide to make our noise measurements. And those measurements were made in the protected sidebands of the WWV time and frequency standard broadcasts that were very carefully protected all around the world. Okay, here we have, and this is from Mark McHenry's power line noise measurements this year. This particular set of data happens to be at 67 megahertz and is measured in a 7 megahertz bandwidth. And these are, most of his measurements in this set were made close to high voltage power lines. And so we see there's a very, very strong 60 cycle and 120 cycle dependence in there. You can see the bursts of noise occurring from arcing on the insulators and probably a good deal of stuff also coming back from electrical equipment that is connected to the power lines that generates noise and then feeds it back into the power lines. Okay, but let's just look at this noise. This is a nice example to use because you can really see the noise here. And we can see that, that there's a system noise at the bottom, Gaussian noise. And that's a very kind of random noise there. And then we can see there are close space bursts of impulses, and we can see there are 20 dB higher than that, some even stronger occasional impulses. So one of the things I want to make a very strong point about is what would happen if we used a wider bandwidth to measure this. Mark used 700 megahertz here, 700 kilohertz, excuse me, bandwidth. What happens when you make measurements of these impulses with a wider bandwidth? Does the signal level go up or down? Well, okay, let's look. Oh, that's interesting. This isn't working. Oh. Well, okay. So the problem here is that I did these slides in old PowerPoint, and this has got the new PowerPoint thing, and so it doesn't respond to timing stuff, so this is a little bit loused up. Okay, so if we have an impulse, here's the impulse. Is this the impulse? Let me see which the... I'm looking for a laser on here. No, that wasn't it. Okay. So, up in the upper left corner there, an impulse is a burst of energy. It's infinitely short in duration and infinitely high in amplitude. And so when we measure this, when we multiply this infinitely high peak energy together with the zero duration, we get a number that actually represents a certain amount of energy. If we look at the spectrum in frequency that this thing produces, it produces a very wide spectrum, maybe hundreds of megahertz wide, and almost uniform. Now, of course, we never get a chance to look at an impulse by itself. We always have to look at an impulse through bandwidth. And so there in the lower left corner, I've said, supposing we had bandwidth B, and what we have is the impulse going up to some voltage. Takes a little bit of time to get through the filter, so there's a little bit of time delay there. And it gets to some voltage V, and then the filter discharges gradually and get down to 0. And of course, it takes an infinite amount of time to get to 0, really, but I just said it gets down close enough to 0. We call it 0. Oh, okay. Okay. Oh, good. So, so here it gets up to voltage V, and then it slowly decays down to T, down to 0 at time T. Now that's an arbitrary bandwidth B. Suppose we measure it in half the bandwidth. Well, what happens is now the filter takes twice as long to respond because it's got half the bandwidth. So that means it's going to take twice as long to get up to a peak, and it's going to take twice as long to decay down to 0. But the peak it gets up to is only half as big. If we use half the bandwidth, we only get half the voltage. And so let me see, does this make sense? We get half the voltage for twice the time. But remember, if we're measuring power, the voltage gets squared. So if we talk about the peak power, even though that's only half the voltage, it's only a quarter the peak power. So we have a quarter the power lasting for twice as long. So with half the bandwidth, we have only half the total power under that curve. And that makes sense because we're measuring only half the bandwidth, and if this is a very long uniform spectrum, the amount of power we should be measuring, the amount of total energy that should be in that time response there, if we measure in half the bandwidth, it should be only half the total power in there. And similarly, if we would measure in twice the bandwidth, now it would go up to 2 times the voltage that we got with the bandwidth. 2 times the voltage, 4 times the power. So we get the peak power now is 4 times as much, but it only lasts half as long. So we've got a matter of 4 times half. We've got twice the power, and that's just what we would expect because we're measuring with twice the bandwidth. Okay, does that make sense? I mention this because people are not used to measuring impulses. Okay, so suppose now that instead of that 700 kilohertz power line noise that we just measured, suppose we measured it with 7 megahertz, 10 times then the bandwidth is going to be 10 times as much as it was before. So that means we're going to add 20 dB to the impulse. We're going to add 10 dB to the system noise. So that means now that the impulses should go up 10 dB more than system noise goes up. So unlike measuring regular signals, when we measure impulse noise with a wider bandwidth, the impulses actually stick out of the noise further. So, and this is going to be screwed up a little bit, I can tell. Well, okay. Now, so on the top is the original 7/10 of a megahertz bandwidth measurement. Underneath is a screwed up picture, which is supposed to have 5 different levels of action in it, but it doesn't. But in that screwed up picture, if you look at the fact that I changed the amplitude scales on it, on the top one, the amplitude, the top of the noise, the top of the Gaussian noise, was about 100 dB. On the bottom one, though you can't see it, the noise is way down there. And so it's at about 90 dB. So the noise did indeed increase from minus 100 dBm to 90 dBm. And the impulses that were there here, they were at roughly minus 65 dBm, this one, and now they're at minus 45 dBm. So the impulses went up 20 dB, the system noise went up 10 dB, but the noise sticks out of the impulses stick out of the noise 10 dB more by going to 10 times the measurement bandwidth. And similarly, if we do the same thing with decreasing bandwidth, say we decrease it by a factor of 10, then we're going to subtract 20 dB from the impulses, and we're going to subtract 10 dB from the system noise. So the amount that the impulses stick up above the system noise is going to go down by 10 dB. And when we do that, looking at the top one, what we started with, and looking at the bottom one, you can see that the impulses have gone down more than the system noise has. So, well, okay, let's go just one step further here. So if we look at these areas where if we look at these areas here, we're getting roughly 8 impulses per millisecond. This is a 35 millisecond time scale across there. And if we were measuring this in, say, the 200 hertz bandwidth that our ARN2 made measurements in, a 200 hertz bandwidth would spread these impulses out to a very wide width. They would be spread out to about 5 milliseconds in duration, 1 over the bandwidth. And that means that all of these impulses here are going to be blended together. They're going to be overlapping now because they're going to be spread out, so they're going to overlap the adjacent impulses. And once you get these impulses overlapping, what happens to them? Do they add up? Well, remember, these are vector quantities, so some of them, because the phase is random between the impulses, some of them will add and some will subtract, and it'll look just like Gaussian noise, just like the Gaussian noise at the bottom. Now, the real question then is, when we talk about system noise here, the Gaussian noise, is that really system noise, or is that just overlapping impulses? Impulses that there's so many at that lower level that they overlap all the time. And of course, the problem is, who cares? Who cares? If you make measurements with a system with a bandwidth such that the noise overlaps, it will look just like Gaussian noise. And it doesn't matter whether it's real Gaussian noise or whether it's Gaussian noise from overlapping impulses. But it will look just like Gaussian noise, and your system will behave just like it was Gaussian noise. Now, if you would have a wider system bandwidth, then some of the impulses now that were overlapping may not overlap anymore, and they may turn into impulses again and come above the system noise. So, here we have a picture I've drawn of 4 different bandwidths here. This is the one we originally started with, 700 kilohertz. Here's 7 megahertz, 70 hertz, 7 kilohertz. And of course, these show far different amounts of noise, kind of. But what's the difference between them? They're measured in a different bandwidth. So what should we think about what's the best bandwidth to make measurements in? Any suggestions? Oh, and actually, I haven't told you the whole problem yet. Even though these noise spikes stick out above the system noise a lot, remember in that first thing with the graphs of the different bandwidths? When they're getting taller, when they're getting 10 times more voltage, they're also getting 10 times narrower. And so I've drawn these things as though we can actually see them. But depending on what kind of a measurement system you have, it may be that once you go to these very narrow impulses now, most of them may not last long enough that your system can even see them. So that's a potential problem. Any other ideas about which bandwidth is the right bandwidth? Oh, okay.
Why not measure where the bandwidth in the detector back is the same as a victim receiver, so that you can see the noise the way a victim receiver will see noise?
Oh.
So you know what effect will be on your victim receiver if you're going to share a spectrum.
Okay, so if you want to get one guy planted in the audience who knows exactly the right answer, that's of course the right answer. Sure. So how do you choose a bandwidth? First of all, if you're making these noise tests to see how a particular system will work, pretty good idea to make the measurements in the same bandwidth so you can see the noise as the victim receiver will see it. Also, in general, if these noise, if you go to a wider and wider bandwidth, the noise the noise impulses are going to become very high. That means, and they're going to become very narrow. The very high means that you'll need a larger dynamic range in your measurement system, more bits in your digitizer and your A to D if you're using a digital system. And also means you're going to have to take data much faster. So there are some real measurement system limitations if you go wider. Anything else that can happen to you? Most people who are making noise measurements like this these days have stopped at about 1 megahertz in bandwidth. And part of the reason in that is because when you go wider, it just is hard to find spectrum these days that is clear for, say, a 10 megahertz bandwidth with no signals in it, that is reliably clear so that you can make good measurements. And what happens if a signal gets in there where you're trying to measure only noise? Well, if the signal is 30 dB above system noise, you're going to see everything below 30 dB above system noise blocked out by your signal. You may miss all of the interesting stuff in the data you're trying to measure because you're now being blocked by a real signal that's there all the time instead of just for tenths of a microsecond. Okay. Now, if you're really smart, and a number of people have tried doing it, the Europeans have tried to do it, it may well be that we don't care about signals like that because we will try to figure out how to digitally excise the signal, subtract it away, process it out, and then we can still see the noise. That's been kind of a dream, and so far I haven't seen anyone who says that they're convinced of the results yet. So partly because you can't tell what kind of a signal you're going to run into. And you may have some very, very complex signals that you have to, in fact, you may have signals that look just like noise. So what do you do then? Okay. So I think that's almost enough on bandwidths. But I did want to make,
10 minutes.
Okay, so I'm going to have to go a lot faster. Okay. So the next thing is, how can you statistically summarize this noise data? And there are roughly three kinds of ways we can do it. We can somehow record all the data if we have a very nice high-speed processor, and we can record the I and the Q channels separately so we can put them back together any way we want and do that kind of thing. That's the raw data. We can record all the data, but that's a very complex process. The next thing we can do is measure amplitude probability distributions. And they're a really good way to do it, but it doesn't have any time statistics. But it gives a good, it says that a certain percentage of the time the level was higher than a certain amount. And it does that for all the levels. Or you can just measure these various averages like we first measured. The RMS average, the V sub D. We have a thing called L sub D, which is the difference between the RMS and the average logarithm of the voltage, or the average dB value of the voltage. And then there's some things like quasi-peak that the FCC specifies for making noise measurements, but it's an absolutely meaningless measurements that makes no sense. But it was back in the days when all you had was narrowband amplitude modulated voice systems. Okay, so here we have some more noise data, similar to the stuff I showed earlier. This is some stuff that Jeff Wetman took a few years ago. And here's an amplitude probability distribution in APD showing, you see a small amount of time, the signals are above this level, and then you see this stuff down here, and you see this bump here in the curve. And you see the Gaussian noise, and this is a special kind of called Rayleigh paper, and it Gaussian noise, system noise plots as a nice straight line there. And one of the nice things about this is that you can see that this particular thing looks like there's a nice piece of Gaussian noise, system noise at the bottom, and these kind of two levels of impulses. Okay, so, and you can't read that, and you can't read that. Here's a system we had for making man-made noise measurements. This was meant to drive in traffic, and that's me, which shows you how old a system that is. This is inside one of the two racks, and we would make three kinds of measurements. This parked in various kinds of neighborhoods, or actually driving through traffic, because what we're really concerned with there is how cars get land mobile signals, or we could even drive over an area multiple times to get noise contour maps of things. And so that was what we were doing there. Okay, and so that's, let me see. That's, ITS made its first noise measurements. This top is the atmospheric radio, following the atmospheric radio noise program. Here was a major report that came out on this man-made noise program. And then we have occasionally made measurements to see whether anything had changed. HS and Dalkey made a set of measurements in, I think, 99 or 2000 or something. Wetman made a set of measurements in, the report came out in 11. But in both of these cases of measurements, the decisions were finally made that there was no need for a big new set of measurements, because even though it showed maybe a slight increase in noise at the higher frequencies, which maybe meant that our model wasn't being followed well, there just wasn't that much of a change to make a big new expensive set of measurements. And let me see. But quickly, I want to show you some of, these are measurements now made across a 24-hour period. And these measurements, these are 10 dB per division here. This is essentially the peak noise, this is the average noise, and this is the median noise level. Median noise level stays very close to system noise most of the time. You see how you can be, how the peak measurements now are 50 dB above noise. You'd think that would be a huge amount of noise, but remember, these are peak measurements and they occur only a small amount of time. And the other thing is, look how much they change. Something is turning off and on in there that makes a 25 or 30 dB difference in noise. And we find this over and over in these 24-hour measurements, where we see large changes in noise due to something turning off and on. And that suggests that you really can't just make one noise measurement and say that's the noise in an area. It makes a big difference whether you make measurements at night or, okay, and when we looked at the atmospheric radio noise, the noise was strictly natural. It was made from lightning storms. Any man-made signals were thrown out. When we went to our man-made noise measurements, we had all kinds of signal sources now that included power lines and fluorescent lights and switching power supplies and on and on. But we tried to throw all intentionally radiated signals out. And now we're talking about what's that noise background look like now? Is it a bunch of small signals that are Wi-Fi signals or unlicensed low power stuff floating around, or maybe even bootleg stuff, or is it, or are they are what we think impulsive noise? For all we know, they're impulsive type of ultra-wideband signals that use impulses to communicate, and so it's not. We don't really have a good model to follow as to what we should call noise and what we should call signals, because some of our signals look exactly like noise now. So that's a thing to think about. And finally, how often should we measure? In the old ARN2 days, we had 16 or 18 stations worldwide, and we just left them turned on. That covered the whole world. Oceans, we didn't worry about because those signals, those noise signals, traveled a long way. On our old man-made noise program, we made signals on highways, we made signals on, but they were in housing developments and stuff like that, but all was outside because radios were outside. I mean, a person didn't use a mobile radio inside a house. Today, we've got wireless, Wi-Fi, non-licensed, and they're used everywhere. They're used inside houses, they're used inside cars, they're used inside shopping malls, they're used in stadiums, they're used everywhere. And so, and each of these is a different environment. So it looks to me like, at very least, we need to make measurements in a very wide range of locations, because radios are used in a very wide range of locations. And then what to do about noise-like signals. Here are several things we can do. We can just measure everything and take what we get, and or we can measure everything, but if there are known signals in there, we can take them out and call the rest of it noise. Now, one of the things the Europeans have done, and there is the ITOR recommendation, SM 1753, they've actually said, you know, if we go to wider and wider bandwidths, what we've been calling Gaussian noise at the bottom end, that I've been claiming is all a bunch of impulses that are overlapping each other now because of the measurement bandwidth, if we go to a wide enough bandwidth, we ought to be able to separate that stuff out, and we ought to be able to eventually get that all reduced to impulses. And the problem is that that never happens. And so there's the Europeans are really worrying about system noise a little bit. And I don't know, that's, there are other things we might try to do. But as I say, I don't really have a clear picture of what would be the best thing to do. So that's a major problem to think about. And that's the end. So.
Very good. Thank you very much, Bob.
Mm-hmm.
I think this is a pretty technical subject, and I think perhaps if you do have questions and follow-ups, the best is to take the break that we now have between now and 1 o'clock, when we'll reconvene to just check in with Bob one-on-one. So we'll be back here at 1 o'clock for the start of the conference, where we'll delve into this a little bit more deeply and actually go up to 30,000 foot as well. Thank you very much. See you in 15.